Since Daniele already presented Kyber on Monday and Can presented dilithium, so I will present you the last lattice-based scheme selected by NIST. So let me just quickly remind you what is a signature scheme. So you have basically three algorithms. So the key generation takes as input the security parameter and return you the public key and the secret key. And then you have two other algorithms, the signature schemes that takes as input the message and the secret key and generates the signature. And afterwards you have the verification algorithms that takes the message, the signature, and the public key and just answer accept or reject. So basically, the signature ensures you that for the people that receive the signature, is sure that the message comes from you. So this is an authentication of the sender, and also that the message has not been changed during the communication. So basically, you have just two people, Alice and Bob. And Alice sends a public key to Bob, or he can download from some server, and afterwards Alice can send a message and a signature, and Bob can just verify this using the public. Yes, normally we have some certificate around this, but we will just forget a little about this. So the two properties, first is the correctness. So the verification algorithm output yes if the message has been signed by the secret key, and so that the verifier also use a public key corresponding to the secret key. And the security means that any attacker which does not know the secret key cannot forge a message, valid pair message and signature. Okay? So let me move on to Falcon. So the NIST decided to change the name of all the algorithms. So for Falcon, it will be FNDSA. And so the main property of Falcon is that this is a Hashing-based signature scheme, and it uses, in fact, the n-true assumption, okay, using a polynomial as Daniele defined on Monday. So I will explain you how we can build a Hash-and-sign signature and what is, in fact, the property or the specific that we, in fact, use in Falcon in order to make it efficient. Okay, so Falcon was one of the three main lattice-based signature schemes that have been selected. So there is dilithium and Falcon, and also Things Plus that has been selected. This is based on only hash function, and we will not go into this detail now. So the main advantage of Falcon is that it is very compact. This means that the size of the public key and the signature is shorter among all other schemes. Okay, so this is in fact very interesting for PKI and certificate, because usually you have in the certificate you have a public key and also a signature that allows you to authenticate the certificate and the public key, and so that means that you can have short certificate also. However, the main drawback of the process is that the signature use, in fact, floating point operation, and this means that you will not use it on every processor, but usually if you use a smartphone or a laptop, it will be the case. And also, however, so we can also mention that the verification does not need a floating point operation. Okay? So here is the performance of Falcon. So I give you also the data in order to compare with the pre-quantum scheme for RSA and ECDSA using Edwards curve. So you see that these numbers are very efficient. And however, if we compare with dilithium, so you can see that public key is shorter as well as signature. And so basically you can see that the signature time and verification are basically as good as for pre-quantum scheme. Okay, and for Sphinx, you can see also that the signature is very large. Okay, even if the public is short. Okay, so that means that the main drawback of lattice-based post-quantum scheme in general is the size of the public key and signature. I think it's not a big deal to have a 1 kilobyte scheme, but it is indeed larger than elliptic curve. Okay. However, we can see that the time to verify and sign are very competitive, and so it's not a big deal to move on to post-quantum scheme nowadays. And so I think it's what companies are doing. Okay, so let me explain how we can build a Hashn signed signature. So in fact, this is a long story. And that began in 1997, but so the idea is to use, in fact, some algorithm and to find a short lattice point to some an arbitrary point in the ambient space generated by the lattice. Okay, so so this is the main building block, and so as input you have some value x that is not an integer combination of the basis element, so this is not a lattice point. And the goal is to find a vector of the lattice that is short and close to x. Okay, so that does not mean that this is the shorter lattice point, but it will not be too far from this. And the main idea, in fact, is just to round each coordinate. Okay, so that means that instead of decomposing this 3.7, so you just round the value to 4 and minus 1.4, you just round it to minus 1. Okay? And so this is a very natural algorithm, and it has been discovered by Babai, and it's called a round-off algorithm. And so its efficiency is quite good, especially if the size of the basis is small. Okay, and so if the size of the basis is small, the solution that we get will be, in fact, close to the lattice point. Okay, so you can see on the picture that here, in fact, we begin with as input the value x, and so we get, in fact, the value s, which is close to x, and it is in the lattice. However, there are also closer solutions to this value. Okay? So this is one of the algorithms that we use, in fact, to solve the closed vector problem. And there is also the problem, but I will look at it a little bit later. Okay, so you can see, in fact, that if you have a basis generated by B1 and B2, in fact, what is important is you can split the whole space into some cell. And according to this cell, in fact, you have only one lattice point in this cell. And according to the cell in which the value x is, you will associate the corresponding lattice point. Okay, so in fact, it will depend on the short basis that you begin with. Okay? Okay, so now how we can Hashn sign generate some signature. So the idea is just to have the public key is just a bad basis of the lattice. So you can generate some short basis, for instance, you can begin with, and use, in fact, some HNF transformation on the basis, and it will, in fact, give you some relatively bad basis. And so you have the short basis will be, in fact, the secret key. Okay, and if you want to sign a message using the secret key, you just hash the message, and you will, in fact, this will give you some value x, and here, and here you will just, in fact, use this short secret key to find a close lattice point to this value. Okay? And during the verification, so you will just, in fact, check two different things. The first one is that S, which is a signature, is in fact a lattice point. So you just need, in fact, the public key to check this. And then you also have to check that the difference between the edge of the message and the signature is small. Okay? Is there any question so far? No, it's good. Yeah, so maybe, so this is in fact the signature that has been proposed by Goldreich, Goldwasser, and Alevi at Crypto 97. Okay, so however, there are some attacks on such scheme, and one of the most efficient has been described by Van Nguyen and Oded Regev at Eurocrypt 2006. So the idea is, so the attack is called the parallelepiped attack, and I think you will understand shortly why it is named like this. So the idea is just to ask for many different signatures, okay? So, we use, in fact, we ask for a signature for the hash of this message. So it will answer and give you the value S. Okay, and once you have the value S, in fact, you will compute the difference between these two, and you just make this vector from the origin of the lattice. Okay? And you can do this for another point. So this will give you some other point here. You compute the lattice point close to this value. And then you will also report here, in fact, this vector from the origin. Okay, and if you can do this, in fact, many, many times. And at the end, in fact, you will see that you will closely cover all the parallelepiped here that you begin with. And in fact, from this parallelepiped, or from the set of all the points that you get, in fact, you can recover the short basis using some clever gradient descent algorithm. Okay, so this is a very important attack because this just uses, in fact, some statistic, and also it has been, in fact, used to make some side channel attack on Falcon, because sometimes, in fact, if you have some side information, you can use them, in fact, to gain some information and, in fact, recover exactly such a parallelepiped. And also, there is also a variant of Falcon that is called Peregrine that has been proposed to the Korean competition for post-quantum scheme. And this scheme uses, in fact, not a Gaussian sampling, as I will explain you for Falcon, but some binomial distribution. And such attack has been also used to attack Peregrine. Okay, so I think it's a very clever attack, and if you don't know how it works, this is just a gradient descent, and it's very efficient. Okay, so this is yeah. Sorry.
How efficient is this? I mean, in this picture, one can see that it's fairly easy, but then in high dimensions, how many points do you need in the parallelepiped?
So I don't remember exactly the correct value, but I think it's polynomial.
Yeah, it is polynomial, and it's just principal component analysis what you do is a standard technique. But polynomial number of points is also quite reasonable. So they could run it in practice. In the paper, they also run experiments, and they show it works in practice.
Yeah. Okay. Is there any question? No? So if you don't know this paper, I encourage you to read it. However, we can in fact prevent this attack, and this has been proposed by Gentry, Peikert, and Vaikutanathan at Stock 2008, and using a very beautiful paper. And so the idea now is not to decode every random point deterministically using the closest to one, but to use in fact some to decode it randomly. Okay. So now when you sign a message, so you generate value X here, and then you try to, in fact, generate a lattice point that is close to this. So you can imagine that you have some ball around the value X, and then so you will have now a lot of lattice points, and you will just pick one of them randomly. Okay, so according to some radius here that we fix. Okay, so if the radius is quite small, in fact, so you will have not too much lattice points, so it will be hard, in fact, for the cryptanalyst to forge signature. And if the ball is much larger, so it will become easier. Okay, so in fact, and if the radius is not too large, so we will, in fact, go back to the previous attack. And so there is some trade-off, in fact, for the size of the radius, but we will come back later. Okay, so you can do exactly the same kind of attack as I described it before. So you construct this vector using the hash of the message and the signature, and you can report it here from the origin of the lattice. You can do this also for another signature, and it will give you also another point. And at the end, so what you will get is that points that will be, in fact, around this ball, and generally in high dimensions are close to the border of the ball. Okay? So this means that now we boils down to the question, how can we, in fact, sample a lattice point around some arbitrary point in the ambient space? Okay, so this is the goal, and the GPV paper proposed one of these algorithms, and we will go back a little bit later on it. Okay? Okay. So now I will explain you how work the N-true scheme, because Daniele mentioned this, that N-true has inspired, in fact, him to generate more hard lattice. And I think it's important to understand how works N-true, because in order to sign with N-true, we need to, in fact, make some difference and some changes in the key generation, and they have not been, this is not completely easy to know how to do this very efficiently. Okay, so this is an N-true scheme that have been proposed by Hofstein, Pfeiffer, and Silverman. And so this use, in fact, two very small parameters. So some value Q that is prime, not too large, but a little bit. And you also have some constant that is some bound, in fact, on some values that you will generate. So an instance of N-true is, so you just pick, in fact, two small, here I give you a small integer, so for instance, these two values, and then you compute, in fact, so the inverse, so G divided by F mod Q, and it will give you some value here. Okay, so this is, in fact, an N-true instance, and this is very easy. And the N-true assumption means that given H and Q, it is hard to recover, in fact, two value U and V smaller than C, the constant C, such that H is, in fact, can be written as the quotient of U and V mod Q. Okay? So this is just a division. However, wait a minute, in fact. So this is, in fact, not a hard problem, because this, in fact, can be described using only dimension 2 lattices, and so it's easy, in fact, to solve such assumption for this kind of problem. Okay, so in fact, we will not use integer anymore, but we will use some polynomial, and now we will, in fact, compute this division, but inside this ring. Okay, so this is the main difference, but so the public key is just, in fact, the division of two polynomial here, mod q. Okay, so let me describe the true crypto system. So for ntrue, you have now two different integers, so q and p, and so q depends, in fact, on the security parameter. Okay, so however, q as it's better if q is not too large, because otherwise there is some attack, and they have been described by overstretch ntrue parameter, and because ntrue has been also used in order to construct a lot of FHE scheme, and they can be broken if q is much too large. Okay, so q is large, but not too large. And now we work with exactly the same ring of integers as I mentioned, which is cyclotomic because d is a power of 2 here. And the secret key is in fact a 2 random element in this ring. And so the coefficient of this polynomial are small, and quite small, in fact. And f is also invertible mod p and q. Okay, so you can think that f can be generated like this. In fact, p is very short, for instance, 3. And so you have +1 plus a multiple of p, and f prime is in fact a short polynomial. Okay? And the public key is just, in fact, the quotient, but now I multiply each coefficient by the small prime p. Okay, by 3, for instance. And to encrypt a message, so it's very easy. So you just, in fact, pick a message. So you encode it using a very small polynomial in RQ. You generate also R in the same ring, also with a small coefficient. And so at the end, you can see that, in fact, the product of H times R, in fact, is basically some uniform value. And so that means that here, you, in fact, is just a one-time pad. Okay, so you just add some random value to the value n. And to decrypt, so the idea is the following. You just multiply everything with small f. So that means that you will get this value and mod q. Okay? And as we begin with only very short polynomial, so we have only short by short is short, and also short by short plus short, it will give you a short polynomial. Okay? But if the polynomial is short, that means that now, so the value that you get, so m, the value here, does not hold only mod q, but it will also hold over the integer. Okay? So here, there is no modulo q. And so to decrypt now, you just have, in fact, to compute everything mod p. Okay, so it's easy to see because, in fact, f mod p is equal to 1, according to how we define f. And here, you see that you have a multiple of p, so that this term completely cancel out, and you just recover m. Okay, so this is a very beautiful scheme, and the difference between ntrue and what we will look is that for ntrue, the secret key, in fact, can be reduced only to the small polynomial f, because it's only what you need in order to decrypt. Okay? Yeah.
Sorry, I'm just not sure. What does it mean that a polynomial is invertible modulo p? Because, of course, if it's a number, it's clear. I was just a bit confused with meaning of. Yeah,
I agree. I've not. So that means that if U is not RQ here, but it's RP, so it will be invertible.
Okay. Okay. Yeah, okay. I see. Okay.
Okay, thank you. So what is untrue assumption? So the untrue assumption is that given H, and so it's difficult to recover two polynomials with short coordinate, so that H is in fact the quotient of these two polynomials. Okay, so how do we can get a hard lattice from this value? So this is the following. So let H be some untrue instances. And so we can in fact define this lattice, so the lattice generated by 1, 0, Q, and H. Okay, this is matrix polynomial. So here, in fact, you have H is a polynomial, and also we see 1 and Q as a polynomial. Okay, so it's a very simple polynomial, and 0 also. Okay, so it will give you a QRE lattices. And so this is, in fact, the untrue lattice and the untrue public. Okay, and you can see that, in fact, a point is in the lattice. In fact, if we satisfy the equation so that U times H is equal to V mod Q. Okay, so this is the definition of the lattice. And in fact, finding a short vector in this basic allows you, in fact, to break and through. Okay, so this has been discovered by Coppersmith and Shamir. And so in order to break and through, they introduce this, lattice. And so they explain that we can break, in fact, and through if you can find a short vector in this lattice. Okay, and if the untrue assumption holds, so that means that this problem is difficult. That means that there is no adversary that can find short vector and find short basis. Okay? So basically the hard lattice that we use. So this is, in fact, a very specific lattice. And however, it's hard to compute small vector on this. Okay, so let me recap that we have up to now. So we can, in fact, generate hard random lattices. So the idea is just to begin with two small polynomials. You just divide f by g, mod p, and mod the polynomial x to the d plus 1. And so you get now two vectors, 1h and 0q, and this will be the basis of your lattice. Okay, so this is a dimension 2 lattice, but with polynomial as coefficient. And then, as Daniele explained, you can always, in fact, rewrite everything in the polynomial basis here. Yeah, and you will get, in fact, a much larger matrix. It will be of dimension 2D now. And in fact, so the polynomial 1 and q is just, in fact, q over the diagonal. Okay, so this is very easy to see because if you begin with a q, so here you will get q times x, so you will get exactly on the second coordinate, and so on and so forth, and so you will get exactly q element over the diagonal. Okay, so some of part of the matrix are very structured, and also for the one in the lattices, it will just give you the identity, and the 0 will be the 0 by 0 matrix. Okay, so in fact this is rank 2 matrix, and so it's not exactly what we have when we speak about module LWE, because module LWE, so for a 2 by 2 matrix, you will have, in fact, random polynomial for all 4 elements. Okay? Here, the untrue matrix is very structured because you have only one random element, and even it's not completely random. It comes from, in fact, the quotient of 2 small polynomials, and all 3 different elements are, in fact, 0, 1, and q. Okay? Okay, so now what is a Falcon scheme? So Falcon is in fact, so we have in fact the key generation. So the public key is some matrix A, which is in fact the public matrix that I was describing before using the value H. And B will be some small basis for this lattice. And in fact, so the relationship between the two is that B is in fact give you some short vector in the kernel of this matrix if you look at the transpose of A. Okay, so this is some trapdoor for the matrix A, and B has small coefficient. Okay, and to sign, it's exactly the same. You generate some value C from the hash of the message. You compute some value lattice point V that is close to C according to the secret basis randomly. And then you just output the difference between C and V. And this is the signature. And to verify, you just check if S is short and if the equation holds. Okay, so it's not too difficult to see that this equation is correct, because if V is a lattice point, so you can in fact see that here I describe it lattice by it's the row, the vector row. So you can see that this is an integer vector that is multiplied by this matrix, and if you do the math, so you can see that this value happen, and as I told you, B times A is equal to 0, so this value cancel out, and so you will recover, in fact, H of the message. Okay? Okay. This scheme has been, in fact, described by Leo Duca, Vadim Lubachevsky, and Thomas Prest at Azure Crypt 2014. And in fact, they described an identity-based encryption scheme, and there is some relation between IBE scheme and signature scheme and hash and sign signature, and so consequently, they also describe some signature scheme. Okay, however, in order to move from this scheme to Falcon, in fact, we have two main ingredients. The first one is how to do the key generation efficiently. And this has been described later in a paper at PQC 19. And also how we can do efficiency, how can we compute efficiently the Gaussian sampler. Okay, so this, I think, one of the more complex part of the signature, and so I just explain you how it works, but I think it's a nightmare, and if you want to implement it, I think it's better to use a reference implementation. So what is, in fact, the main ingredient for the key generation? And both the key generation and the improvement for the Gaussian sampler, in fact, reuse basically the same kind of ID. And this is exactly what we try to explain you. Okay? So the idea now is that we have, in fact, so the basis H, if we forget the two other elements. And in fact, we want, in fact, to construct the short basis B, okay, so that this equation holds. Okay, so this is not too difficult, in fact, to see that a first part of the basis will be given by small f and small g. And if you check exactly, so you will see that it will give you 0. Okay? So, however, we need, in fact, another vector that satisfies this equation. And so this means that we want to solve, in fact, what is called the full trapdoor problem. Okay, so the full trapdoor problem is that now you have a part of the basis, and you want to, in fact, find another pair of vectors, which is called capital F and capital G, so that the same equation holds. Okay, so capital F minus capital G times H is equal to 0. Okay, so however, this is not a completely easy problem. So, but since you have some information, we already know, in fact, part of short element, so f and small f and small g. And so the idea is now to recover some polynomial in this ring so that this equation holds, and we can also see that small f and small g and capital F and capital G will also satisfy this equation. Okay, so this is not too difficult to see. This is just because, in fact, the two lattices must, in fact, have exactly the same determinant. Okay, and since we know that the determinant of the matrix A, since we have only Q on the diagonal and 1, and 0 on some other part, so if you compute the determinant of this 2 by 2 matrix, so you will see, in fact, that you get Q. Okay, so now we just want to satisfy, find capital F and capital G so that this equation holds. Okay, so but the main difficult part is that here, in fact, F and G must be in this ring. Okay, and there is no mod Q here. Okay, and so this is one that makes the problem, I think, difficult, because you can see that if we have, in fact, some reduction mod Q somewhere, in fact, the value will be short during the algorithm, and it will be easier at some point. Okay? So there are previous techniques to solve this problem, and some of them use resultant or HNF, and the running time for this algorithm is n cube, and the space is n square. So this is polynomial time and space. However, if you want to have some very efficient scheme, they are not efficient. Okay, because in fact, n to the 3 will be around 2 seconds, and so you need 2 seconds to generate the secret key, and it's not exactly what we want. And also the space is huge, and if you want to integrate the key generation into some embedded device, maybe it's too huge. Okay, so the idea to have a more efficient scheme is, in fact, to work with what is called the tower of ring. And so this is a case if you begin with a power of 2 cyclotomic field, and even power of 3 or something else, but in power of 2 is a case, and maybe it's a simpler example. Okay, so we work with this cyclotomic ring, and so inside this ring you have another ring, which is that one, so the dimension is divided by 2, and so I will explain you how we can in fact navigate into this tower ring, and at the end here you have just the ring of integer. Okay? Yeah, Otek?
When you wrote n cube space and n squared time, is n d log q or?
What is n?
When you wrote previous techniques, you needed O of n cube time and O of n squared space. Does n correspond to d log q or?
For me, d is a dimension, and it's another parameter. It's not log q. Q is one parameter, and
so the n is just d then? Yeah,
it's just d. And yeah, and you have in fact d elements. So for Falcon, so d is 2 to the 9, and no, it's 9. Sorry, and 9 and 10. Okay, so it's a small value. You need, in fact, to work with the field norm. So we need, in fact, to define it using the number field here. And so the norm allows you, in fact, to go from this to this ring or to this field, in fact. And the idea is just you map this polynomial into this product of polynomial, and so f of x is in fact just f where you evaluate it at minus x. Okay? And this is very convenient to solve the problem. And it is basically also the same kind of tool that is used during the Gaussian sampling. Okay, so the idea is to work with this tower of field, and this is a case for n-true and Falcon in general, but there is also some parameter. I don't know if you know n-true prime, but in n-true prime there is no such tower field, and so it cannot be used directly. Okay? So for n-true prime, it was the purpose of the designer do not use, in fact, such scheme because they thought that maybe it will introduce some weaknesses into the design. Okay, so now we have to solve the equation, and as remind you, so here it's over Z and not ZQ. Okay, and we want to find the value f and g like this. Okay, so the idea is that assume that we have solved the problem over the sum of this, so the ring just before what we want to recover f and g. And so we recover, in fact, capital F prime and capital G prime. And we have some value here and here, which are, in fact, value in this ring. Okay, so they correspond to the norm of some element. And in fact, from the definition of the norm here, so I define it using the field and not the ring, but it's exactly the same. So in fact, this value is f time, and this value here also is small g times g to the x. Okay, and so you can in fact see that this value in fact correspond more or less to capital G, and this value will correspond to capital F. Okay, so the only difference is the 1 here. However, you can multiply by Q, it does not change anything. Okay, so the idea now we know how we can, in fact, if we can solve the problem in some subring, you can go from this subring to the ring just above. Okay, so this is the main tool. Okay, so the idea now is to begin with small f and small g in this ring, and you just apply the norm up to the last ring, so you can apply it 9 times. And so what happens when you go from this to this element? So the idea now is that f has a degree d polynomial with small coefficient, but now when you compute this value, so the degree of this polynomial is half. However, the coefficients are twice larger. Okay, this is the case because, as I recall you, it's just f times f to the x, and f to the x has also small coefficient, so the coefficient basically double when we go down here, and the degree is decreased by 2. Okay, so at the end, the degree is 0, so we have just element over z, and so we have this value, and now if you want to solve the equation, so it's very easy to see that, so the equation is just, in fact, some Euclidean, extended Euclidean algorithm, because you have now 2 co-prime value, and so you just want to recover the Bezout coefficient. Okay, and once you have solved and recovered the Bezout coefficient, so now you just have to go up into the tower field. Okay, so this is the idea of the algorithm. And more or less, I will show you the implementation. It's closely related. Okay, so now it's a recursive version of the algorithm. So here, so you can see that for n equal 1, so n is yeah, I agree. N now attack is 2 to the d in general. So at the bottom of the recursion, so n is 1, and so you just have, in fact, to solve to recover u and v, and these are integer. However, the main problem is that, in fact, the f and g are no more very short. Okay, as I told you, when you go down, the coefficient double at each time, and so at the end, you have, in fact, the norm, the absolute norm of the element f and g, and they are quite large. Okay, so you need to have some trick, in fact, to solve the Euclidean algorithm in n. You have to split all the elements into using some RNS, for instance, implementation, and or some CRT, so it's exactly the same, but it's doable to do this very efficiently. Okay, so once you, so this part of the algorithm is the recursion. So you just compute, in fact, the norm in the subring just below. And then this is call, the recursive call. And so you go down, down, down. At the end, you are in some over Z. You solve the problem. And now you just have to go up. And to go up is exactly what I explained you. You just multiply the polynomial here that you get by this one. And you just multiply it. You have just some modification to do this, but they are very efficient. Okay? And so that means that the coefficient of the polynomial here can be quite large at the end. However, the idea is that you can, in fact, reduce, since f and g will be a basis, you can reduce this second vector using the first vector. Okay, it will not change the basis. And this is a very efficient step that can be implemented. And basically, at the end, you get some, so the value of small f and small g have coefficients that are below 20. And for capital F and capital G, they are a little bit larger, but it's 120 at the end. Okay, so it's quite short compared to the value Q. So the value Q for Falcon is 12,289. Okay, and it's not, so it is a very significant improvement because before, in fact, this is a 100 improvement in memory. So you go from 3 megabyte to 30 kilobyte, and also you gain a factor 100 in time. So you go from 2 seconds to 20 milliseconds. Okay? So this is for the key generation, so it's really a huge improvement. And now I will explain you so the idea for the second ingredient, that is the Gaussian sampling algorithm. Okay, but in fact, we will also use this tower of subring to make it more efficiently.
Can you maybe say something about the asymptotics of this improvement?
Or you just gain some factor D, or maybe I have not. You switch maybe D to log D or something else.
Okay.
A little bit more, but basically the idea.
Okay, thank you.
Okay, so I described you at the beginning the round-off algorithm to find some values that is close to a lattice point. Sorry, a lattice point that is close to some random value. So in fact, you can see that we are in this situation, but there are also another algorithm that is called nearest plane algorithm. So the idea is always the same. So you begin with the same operation, and then you will update it at each point. So you begin with the last row of the lattice, and from the last to the one, and you do some computation, but basically is so you try to optimize this more efficiently. Okay, so these two algorithms have been described by Bye-Bye, and so the difference is that here you have something that is very parallel, because for each coefficient we round the coefficient. So you can do this for each coefficient in parallel. Here you can see that this is inherently sequential, because you need to have the value of TG to compute the next value. Okay. So this algorithm usually is slower than that one. However, this algorithm outputs you some vectors that is closer to the point that you begin with. Okay, so this is very important. And the main important things that you have to look at is that here, in fact, you need to compute some Gram-Schmidt orthogonalization on the vector. Okay? So the Gaussian sampling problem is the following. We can express this as follows. You have some basis B, you have some value C, and you want to compute, in fact, a lattice point Z, so that the difference between the two is small. Okay? So this algorithm has been described by Klein, and in fact, you can see that is closely related to the nearest plane algorithms that I described before. And in fact, the only thing that is different is that here before we have some, in fact, takes the integers that is closer to some value. However, here we in fact have the value here, and we compute in fact a discrete over Z point, and so this is a Gaussian sampling over Z and not over some lattice. Over some lattice that is Z, but it's a very simple lattice. Okay, so you can generate some value, so it will be 0, minus or plus 1, plus or minus 2, etc., etc. And so it's a random value that you inject into the algorithm, and it will allow you, in fact, to generate some random element in the ball. Okay? So there are, in fact, 3 different algorithmic techniques to generate Gaussian sampling. So the first one is here, in fact, you can use here the nearest plane algorithm. So this is exactly what, again, Tripp-Eickert and Vaikutanathan did. So this algorithm gives you, in fact, a very high quality. So the quality of the algorithm means that the lattice points that you generate is very close to the points that you begin with. And so the complexity of the algorithm is here. Okay? So the second algorithm is called the randomized Randolph algorithm. So this corresponds you to exactly the randomized version of bye-bye algorithm. And so, however, the main drawback is that the quality, so the output of this sampling is not very close to the point that you begin with. It can be quite large. And so this means that the quality is lower. However, the running time are quite good. Okay, and at IACR 2016, Leo Duca and Thomas Prest proposed, in fact, a new method to take into account, in fact, the tower of subring that you use. And in fact, the quality is now quite good, and the complexity also. Okay, so you can see that, in fact, basically, it has the same complexity as Eickert sampling. However, the quality is better. Okay? So what are the 2 main ideas of the fast Fourier orthogonalization? And it will maybe explain you why it is called like this. Okay, so the idea is always to work with the subring, or to use, in fact, the norm field. And in fact, you can see that you can separate the 2 parts into, into 2 different parts. And the matrix also will be organized like this. Okay, so basically it's just the same kind of matrix that you begin with, but you exchange the row and the column of the basis, and it will give you that way. Okay, so this is very similar to what is done during the Fourier algorithm, and this is the reason why they called it fast Fourier orthogonalization. Okay, and the second step is that you just have to orthogonalize, in fact, the second row using the first one, and so this is a classical step in lattice. Okay, and you use, in fact, the 2 main ingredients. So you rearrange the matrix and you orthogonalize it, and you did it exactly for each different step when you go down the tower of rank. Okay, so this is we use exactly the same kind of ideas. Okay, so you can see that we have something that is quasi-linear in the dimension, in order to compute the matrix L that we need. And also, this can be improved using some FFT, working with some FFT. Okay, so this is mainly the main reason why we have to work with floating point algorithm. However, the floating point algorithm gives us some challenges to solve because floating points are not real, ideal or real. And so it will give us some discrepancy between some ideal Gaussian distribution and the distributions that we generate later. And that's the reason why we have to look at the security of the scheme. And so let me explain you this graph. Okay, so here we have the standard deviation of the Gaussian that we generate. So basically, it will represent, in fact, the radius that is described at the beginning of my presentation. So this means that the radius of the ball where you are looking for some lattice point. Okay, and so if sigma or if the radius is too large, as I explained you, so you have a lot of lattice points around the value C, and consequently it will be easier for the adversary to forge signature. Okay, so we need in fact to have a sigma or the radius of the ball small enough so that it will not become too easy to the adversary. And so usually when sigma is too large, so it will not give us some hard instance and it's easy for the adversary. Okay, however, the value sigma does not be in fact too small, because as I told you, if the radius is if sigma is 0, for instance, so you will in fact, so it's like if you determinize the randomized algorithm, and so you will go back to what I described before and the parallelepiped attack. Okay, so we need to have sigma like this, and so if sigma is very large, so the security, this is the security parameter, so the security is low, and if sigma is very small, so the security here will be large up to some point. Okay, and here in fact, you can see that we have a different curve that will represent, in fact, how the distance between the ideal Gaussians that we generate, and the ideal Gaussian. Okay, and so in fact, you can see that the best way, in fact, is to work with such curve because so you can still have a very short standard deviation. So a small radius, and in the same time, you can also have a very good security, Okay, so this analysis has been done by Thomas Prest at Azure Crypt 2017, and it uses, in fact, Rappe divergence in order to show this result. And the main idea is that to use Rappe divergence is that before, if you use only the standard, the statistical distance or the Kullback-Leibler divergence, in fact, the number of it's only take into account the security parameter and not the number of queries that you are allowed to do. Okay, and here for the NIST competition, the number of queries is limited to 2 to the 64, and it's why, in fact, it's more interesting to use this value. Okay, so in terms of security, you can gain, in fact, 30 bits of security using the analysis that Thomas introduced. Okay, so let me just conclude by give you some advantage and disadvantage of Falcon. So this is a post-quantum secure scheme. So it's the security, the efficiency are competitive with RSA and EDDSA. I agree that the size of the signature and public key is larger. However, if you compare with RSA, is not too large. It's larger for elliptic curve. But in fact, I think Falcon is a very interesting scheme because there are still many open questions to solve to make it a little bit more efficient. Okay? And so one of the main drawbacks is that we still use a floating point for the signature scheme. In fact, we know how to remove the floating point during the key generation. It's not too difficult. However, during the signature process is much difficult. And also, it means that the side channel security of Falcon is more difficult to evaluate, and so that means that sometimes there is some attack. So there are very interesting schemes that have been described quite recently, which is called Raccoon, that try to have a masking-friendly scheme. However, the value queue is quite large compared to dilithium, and so it's not as efficient as Falcon. There are some other way to have more efficient scheme and to get rid of the floating point evaluation. So, in fact, one interesting proposal is Mitaka scheme. So in Mitaka, we use, in fact, some kind of samplers that are in between the Packard sampling and the Klein sampling. And the quality is quite good, and it will, in fact, remove all the complexity due to the fast Fourier orthogonalization. Okay, and in order to make Mitaka as efficient as Falcon, so the idea is to have a more efficient key generation algorithm, and so the key generation has to be updated a little. Okay, so let me conclude. So Falcon stands for fast Fourier lattice-based compact signature over untrue. So you can also use it to construct some identity-based scheme. So the main tools that we use in order to improve the key generation and the Gaussian sampling is to use the tower field when d is the power of 2. We also use it in order to have an LLL version for rank 2 module. So it's also nice, I think. And in a security point of view, there are, I think, two main results that are interesting. So the first one is a result by Damien Stelle and Ron Steinfeld that tried to propose, in fact, an untrue signature using some standard assumption. However, the scheme is not quite practical, and in fact, the value F and G that are small in N2 now, the coefficients are much larger. And so it means that the value H, in fact, is completely, you can prove that is statistically indistinguishable from a uniform value. And the second kind of result is the result by Alice Pellemari, Damien Stelle on the security of the untrue assumption, and they try to make some connection between the untrue assumption and the difficulty of hard lattice problem. Okay, thank you for your attention.